All right, so one of the things that our new state standards say you need to know is how spectra relate to the Bohr model of the atom and our understanding of energy levels in the atom. First thing we need to understand is there's three different types of spectra that you see. There's a continuous spectrum, an emission spectrum, and an absorption spectrum. Start with the one that we all know well, the one that you learned back in middle school or elementary school where you put light through a prism and it breaks down into a rainbow of colors. That is a continuous spectrum. And in a continuous spectrum, you have every wavelength of light. And if we look up here to the picture, you can see that there are no breaks in that spectrum. It is continuous from one end to the other, thus the name continuous spectrum. They are produced by gases that are under pressure or solids and liquids when they're heated. Think about a light bulb, as in the picture above. It's got a solid filament in it. When that solid filament is heated, it produces a continuous spectrum of light. Emission spectrum are very different. In an emission spectrum, you only have a few wavelengths of light being made. We're not producing every single possible wavelength of light. We're only producing some very specific ones. If we take a look at our example here, we have one little wavelength in the red, one little wavelength in the yellow, a couple of greens, a blue, and maybe one or two up there, maybe three in the violet. We are producing very specific wavelengths of light. We are not producing everything, as you see in a continuous spectrum. Now, these are produced by gases that are under low pressure, very low density gases, where there aren't any collisions between the particles. We could take gases, for example, and put them under very low pressure in tubes, excite them with electricity to heat them up, and they'll produce these very specific wavelengths of light. A continuous spectrum is the way that your standard light bulb works. The emission spectrum is the way that neon lights work. You put neon gas into that tube under low pressure, you excite it, you heat it up, and it starts producing very specific wavelengths of light that give it very specific colors. Continuous spectrum produces white light, whereas those things that produce an emission spectrum produce some very, very specific colors, like you see in neon lights. The third and final type of spectrum is an absorption spectrum, and it's different from the other two in that we're not talking about producing wavelengths of light, we're taking wavelengths away. We're removing light from a source. So we start off with something like a regular light bulb that's producing a continuous wavelength frequency. It's got every color in it. It's got your red in it, and it's shooting that red light over towards your gas. It's got the orange. It's got the yellow. It's got the greens. It's got the blues. And it's got the violets. It's got the whole spectrum in it. When this continuous spectrum hits the gas is actually going to absorb some of that energy. It's going to absorb some of those wavelengths. So let's say it absorbs the red. That red comes in here, gets absorbed by the gas, and then it kicks it back out again, but it very, very rarely kicks it out in the same direction that the original wave came from. So it kicks it back away from where your prism is. So in the end, when you look at your prism, you see your orange, you see your yellow, you see your green, you see your blue, you see your violets, but you're missing the red. Okay? There are wavelengths of light that have been removed. These show up as dark bands in the spectrum. And if you look between the emission spectra and the absorption spectrum, the ones that are missing are that gas's wavelengths that it tends to produce. So if your gas would have produced these specific wavelengths in an emission spectrum, when you do an absorption spectrum, those will be the wavelengths that are missing. So they do go hand in hand with each other. Now, why are these things so important? Well, it comes down to the Bohr model and the idea of energy levels. In the planetary model, we had a nucleus, and in that nucleus, we had all the protons and the neutrons. And everything was fine with that. Okay, the evidence to this day tells us that that is correct. In the nucleus, you have this densely packed cluster of protons and neutrons. But out in the electron cloud, in the planetary model, we have these orbiting electrons. It works very much like the planets orbiting the solar system. Well, orbiting bodies crash into what they orbit. It's just the way orbits work. And electrons don't do that. So there had to be something more to it. Had to be something more than just them orbiting the nucleus. There had to be some very specific places that they could orbit. Now you think about a solar system. A planet can orbit almost anywhere in that solar system. It could be close to the sun, it could be farther away from the sun, and there's no set rule as to where a planet has to be. What Bohr theorized is that there maybe for electrons has to be a specific location that they have to be in. It's not that they can just orbit anywhere. There are specific set distances from that nucleus that they have to orbit. And those specific set distances were the energy levels. That there were specific regions, specific distances from that nucleus that that electron had to be. So in other words, our little electron can orbit that nucleus, but it has to orbit either here in the first level, in the second level, the third level, or the fourth level. There is no in between. It can't orbit anywhere else but in those very specific, very discrete energy levels. And what this basically does is brings quantum theory, quantized energy into the atomic structure, moves it into the more modern era. There's also a great way to explain these spectra that we saw, these emission and absorption spectrum we saw. This is hydrogen's emission spectrum. It produces 4 very specific wavelengths of light. The idea was that when this electron is excited by heat or electricity, it's going to bump up into a higher energy level. Continue to excite it, it'll bump up to the next energy level. Excite it some more, it'll bump up to the next energy level, and so on. Put in another level 5 in there. So it'll match my spectrum up here. Again, the more energy you give it, the higher it's going to go. When that electron's energy is released or removed, say you shut the power off, you allow the gas to cool back down again, it's going to have to re-release that energy, and it re-releases that energy as photons of light. This one, perhaps, is the 410 nanometer wavelength of light that we see right here. As it goes from this level back down to this level, it's going to have to release some energy, and that is the 434 nanometer wavelength of light that we see there. As it goes from level 3 back down to level 2, again, it's going to release energy. And this is that 486 nanometer wavelength of light we see here. And then as it finally drops from level 2 back down to level 1 again, it's going to release that 656 nanometer wavelength of light. Every level it drops down shows up as a specific wavelength of light in that spectrum, that emission spectrum for hydrogen. And it works very well for hydrogen. It shows exactly the energy levels the electron's bouncing through. But the problem is it only works for hydrogen. And there's some other issues that, as we'll see, come up with the modern model, the quantum mechanical model of the atom, that has to be corrected. It's not just as simple as electrons moving in circular paths at energy levels. It's something else has to change. But that is how these spectrum relate to the Bohr model of the atom. It is used today in identifying the composition of planets. We're looking at specific wavelengths of light that are being produced, or use it when we try to understand stars and clouds of gases in space. We know, for example, that large nebula are composed of hydrogen gas because when we analyze the spectrum of light that they produce, it fits hydrogen's line spectrum. so we know that the gases that are in those nebulas are composed of hydrogen. These specific line spectra cause certain chemicals to produce certain colors when they're burnt. Again, as these electrons are bounced up and back down between energy levels, and we heat these substances up, they will produce very specific wavelengths of light that combine together to produce very specific colors. We use this in something called flame tests to figure out what the composition of a particular substance is. We'll do some of those in class. It's used in making fireworks. When they want to make a firework, for example, that's blue, they will use a substance whose line spectrum produces a bluish color. Things like that.